A single warning light activates on a factory control panel. Beside it, a bold tag reads 99% accurate. So here's the question. If this alarm is 99% accurate, how likely is it that something is actually wrong? Here's the contradiction. A system can be correct in more than 99% of all checks, while most of its alarms still point to normal events. Both statements are true because they use different denominators. To see why, let us build a simple hypothetical model. Imagine an automated system that checks 10,000 machine cycles. This is a simplified example, not a real specification, so the numbers stay clean and easy to follow. First, the base rate. Base rate means how often the real event actually happens. In this model, a true fault occurs in only 0.1% of checks. That is 1 in 1,000. Now, the first calculation. 0.1% of 10,000 equals 10 real faults. Out of 10,000 cycles, only 10 actually contain a genuine problem. The other cycles are normal. Next, the normal group. 10,000 minus 10 equals 9,990 normal checks. This large group is where a small error rate can quietly produce a lot of false alarms. For visual simplicity, assume the system detects all 10 real faults. That is a simplifying assumption. Real detection is never perfect. Each real fault triggers a genuine gold alarm signal. Now watch the normal group. Among 9,990 normal cycles, the false alarm rate is 1%. A false alarm means a normal cycle wrongly flagged as a fault. 1% sounds small. But here comes the reveal. 1% of 9,990 is approximately 100 false alarms. A small rate applied to a very large group produces a surprisingly big number. Add them together, approximately 10 real alarms plus approximately 100 false alarms equals approximately 110 total alarms lighting up on the panel over the 10,000 checks. Now the key question. When the alarm activates, how often is it right? Divide the real alarms by the total alarms. Approximately 10 divided by 110 is about 9%. So, in this hypothetical model, only about 1 alarm in 11 corresponds to a real fault. The system was correct on more than 99% of all cycles, yet most of its alarms still point to normal events. Let us organize this in a 4-cell outcome matrix. Top row is real faults. Bottom row is normal cycles. Left column shows alarms. Right column shows no alarms. Every check lands in exactly one cell. Notice which cell is huge. The correctly rejected group holds about 9,890 normal cycles. That is why overall accuracy stays so high, even while the alarm column contains so many false alarms. Here is the trap. Overall accuracy answers how often is the system right across everything. Alarm reliability answers a different question. When the alarm rings, how often is it right? Same system, different denominator. A quick second example. Imagine a generic data stream scanned for rare glitches. If genuine glitches are extremely rare, even a tiny error rate on the normal stream can outnumber the real ones in the alarm list. So use a 3-question evaluation method. First question, how often does the real event occur? That is the base rate, the foundation for everything that follows. Second question, how many real events does the system actually detect? Third question, how many normal cases does it flag by mistake? These 3 numbers together tell you what an alarm really means. Improving a system can require trade-offs. Lowering false alarms may raise misdetections, and vice versa. There is no universal setting. In this model, the numbers change if any assumption changes. So back to the original panel. One warning light, 99% accurate. In this model, about one alarm in 11 is real. Always ask which denominator, and a small percent stops fooling you.